I can throw this out here too. If, technically speaking, can you plug infinity in for X? Not really, right? But could you plug in really, really big numbers for X? Yeah. So what would happen if you plugged in bigger and bigger and bigger numbers for each of these X's? You're dividing 5 by really big numbers. This entire term is going to be approaching 0. 8 divided by really, really big numbers is going to turn into 0 as well, which really is just saying the limit here is 0 minus 7 plus 0, which is where you get the -7 from. I would handle something like E similar to that. If it's different terms, if it's one full fraction, I would think Bobo Button needs DC.
Thank you.
Other homework questions we ran into?
What about the 1 in 2E?
Which one?
The 1 in 2E, like
In
I know
2,
the other one turned to 0, but what about that 1? Like, what do you?
yeah, the other 2 terms would turn into 0. The 1 would be left over. But this first one, the -2x cubed, really screws stuff up because of that being the highest exponent, which basically means that it's going to end up going to infinity even with that 1. Because if you plug really, really big numbers in for X here, this first term here, I can't even circle that. That's not working. That first term would be massive. It would basically go to infinity. So the way I kind of think about some of these is if I divide by a really big number in this term, that one's going to turn to 0. Divide by really big numbers in that term, it's going to turn to 0. 1's going to do nothing. But if I plug in really big numbers into X cubed and I'm cubing massive numbers, this term is going to go to infinity. And so even though there's that +1, infinity plus 1 is just infinity, a different form of it. So that entire thing would then be infinity. Other homework questions?
On the exponential limits.
Yep, down here.
You said you wanted us to try to figure that out without a calculator?
If possible, yes.
How would we do that?
I know, like, for example, number 1 here, that an exponential function in general looks like that. And when we looked at exponential functions, this part is what told us the asymptote. So really, I'm just thinking a very brief sketch of this would be asymptote at 1. And it would be an exponential function going up. So the limit as we approach infinity means I'm tracking that. That is then headed off to infinity. However, if I asked you the limit as X approaches -infinity, that's where you would track this part that's getting closer and closer to 1. So it depends on which end they're talking about in the graph. So that's kind of why I draw a sketch real quick to help me with that. Other, yeah.
Right. On 2G,
Mm-hmm.
so I know it was like bigger on top.
Mm-hmm.
That would make it like, that would be none.
Mm-hmm.
So would it be -infinity because you have to look at because it's an odd exponent and there's a negative in front?
What I would do in that case, you could try to draw a sketch. To be honest, the ones where it's none like that, I always just graph it on my calculator to see where the ends are going and track it that way. In most cases, when it is bigger on top, you're going to end up checking a calculator.
Okay, thank you.
Mm-hmm.
How do we figure out like on the exponentials again, like 5 and 6? Like
those are different. I threw them in there just to kind of see what people would do. A lot of people looked at your calculators to see where they were kind of leveling off. But these actually, and I did want to talk about them, they follow Bobo Button Eats DC, even though they're under square roots. So if I'm looking at 5, this one is an exponents are the same, so I would divide my coefficients. So 3/1 just gives me 3. The only difference is then your answer includes the root. So rather than it just being 3, My answer is actually the cube root of 3 because they're both under that.
Okay.
And then 6 is interesting because the root's only on the top. So technically, if you're square rooting a squared, what's the degree?
Just 1.
Right? So that's a 1 on top, technically, even though it's a square root of a squared, but it still reduces to a 1. It's a 1 on bottom. So this is a divide your coefficients out front because technically they're the same, even though you have to kind of think in terms of reducing. So this one would actually work to root 3 over 2. Those are interesting ones, but I threw them on there just to see how people would look at them. You can look at a calculator, but it's not going to give you the roots for that.
Is there a certain time where you would recommend us using the end behaviors chart or the like Bobo Botten eats DC stuff?
Yes, it is the difference between what we call rational functions, which is, I'll pull this up. The rational functions where it's a fraction, that's where you want to use your Bobo Botten eats DC. And then if it's not a fraction like that, it's just a polynomial, that's when you want to use your end behavior chart. Okay. Other homework questions? Are we okay? All right. If we're all good there, then I'm going to move on and talk about our last set of notes. While I'm pulling this up, our test is Friday, Monday for our last test. I did also, and I'm going to send an email out to everyone. I made sure that the Unit 8B test was open. That was our previous test on solving. So that will be test corrections. Seniors, that will be your last set of test corrections. I'm not going to make you do Unit 9 test corrections. You will have taken the test by the time that you are done Wednesday. But seniors, I'm going to make that optional. So if for any reason my seniors want to do limit test corrections, aka an extra 10 points on your test grade, if that helps your grade average, let me know. I'll get that opened up for you so that you can do it before you're done Wednesday. Seniors, you should also see that I've gone in and excused anything 10.1 out, which is also excusing the limits test corrections. So that can either be excused if you don't want to do it, or if you want to do them after that test, let me know. We'll just see where we're at. I'm about to go in and drop a quiz for everyone. This is the part of the year where if we were in class, I would be telling you, make sure you are checking your grade book. If you're missing something, if there's a grade that's wrong, if you turn something in later, I'm really trying to stay updated. I should have everything in that was due by today, including that last limits quiz, but if something's off, just let me know, okay? We are going to today speak about continuous and discontinuous functions, which is page 306 in your notebook. This is the last thing. This will be on your test. And I will jump on at 9 on Friday to run a little review session before the test. You don't have to take it at a particular time. You can just take it. I think I made it a 2-hour window. It just slightly longer. I think it's 13 questions, and I just want to make sure everyone has enough time. And also, before I jump into continuous functions, things that we've talked about, the test will look very similar to the limits quiz, which I feel like we all did pretty well on, and everyone seemed like it was pretty normal. There's that big graph question, and then just if I'm going kind of mentally through topics, we did limits by plugging in, we did limits using factoring, we did limits using conjugates, we did complex fractions, we did a few trig things, but don't expect I know that trig page was super overwhelming. I wanted to kind of pull back in some of the trig stuff, and I expected there to be a little struggle, but I'm not going to be throwing 25 trig questions at you. So I'm basically doing 1 on each topic, potentially 2 trig and 2 limits at infinity, because those weren't on the quiz. And there will be more stuff on the continuous function stuff as well. Any questions about what is on the test? We all good? All right.
Can we
And
just
that-
jump
What's that?
Should we just like as a review, just like go and do the problems that we didn't do for homework?
Yeah, you can do that. Let me see if I put anything in here at the end. There are a few on page 309 that have sines and cosine. Actually, 309 is not bad. There's some factoring, there's some conjugates, there's some trig limits. There's a few questions there. Honestly, like if the quiz was okay, I would just make sure you know the basic trig stuff, like some basic substitutions and the 2 special trig limits, the infinity stuff we just went over, and the continuous stuff we're about to do, and you'll be fine. So I wouldn't worry too much about overly reviewing because it's been such a short unit. We kind of went real quick, and then that's all together. Okay, so I'm going to get to continuous functions here. And I'm actually not going to do a whole lot with notes on this. It's going to be pretty quick, just so you know. And then we will jump off and you'll have your, I think that's the last homework for seniors. Yay. You're almost done. Okay, so here's one of the major points of limits. Limits help tell us if a function is continuous or not. And having a function that's continuous for the purpose of calculus really matters. And knowing whether a function is continuous or not. So the kind of jargon on this, the notation is going to throw you off for a minute, but you just kind of have to stick with me. There are rules to what makes a continuous function. 3 things have to be met. And if you remember, and I'm actually going to in a minute go back to one of the previous pages that I told you to maybe go over for limits on graphs, the way we've been setting up the limits on a graph will really help you to tell if something is continuous or not. So I'm going to walk you through that in just a second. But our 3 things for a limit or for a function being continuous at a point. 3 things. F of that point must exist. In other words, if you look back at the graph and there's 2 open circles, that doesn't count. Or you see an example right here. There's a hole in the graph right here at C. That is not defined. That would be a reason for that being discontinuous. The second thing that you have to check is that the limit at that point exists. So you would check coming in from the left, coming in from the right, that they are coming in and meeting at the same number. So that limit must also exist. And then the third condition that we see here is that the value of the limit must equal the function value. So visually speaking, this is what we're looking at here. Here are our 3 ways that you can be discontinuous, not continuous. The function value is not defined, where you have a hole in the graph. The limit is not defined, where the left side and the right side come into different values. Or you have a function value, which is this third one. You have a closed dot, and you have a limit. But notice in this third picture, they're not going to be the same number. That's also a problem. Okay? So before we do it with any equations, I want to show you what this looks like on a graph. So we are going to scroll for me and for you, flip backwards to page. I wish I had the page number, but I forgot. This one right here, 285. And I'm going to rotate this page real quick if I can.
Are these notes in our binder, or do we need to print them off?
Nope, they're in your binder. Whoops, I rotated the wrong way. That was page 306, I believe. And this is page 285, but we're going to use this to talk about continuous, discontinuous. A lot of you did this as practice for your graphs, but this is exactly how I would kind of set up and test if something is continuous or discontinuous. This is also how I would probably test it on an actual test. So just forewarning. This would be a great question for me to put on the tests for you to tell me visual limits from the left, from the right, the function value, and so on. Remember when we talked about this page, and I'm going to zoom into this a little bit for you, we said these are kind of going in sets of 4. So let's just, and we've done this already, so this should be familiar to us. Let's look at 1 through 4. If I can answer questions 1 through 4, I can also tell if this function is continuous at 1. So we said, all right, here is 1. what would be the limit as we approach 1 from the right? Anyone shout it out. Can we see it? Or
Is it
2? Yep. And what would be the limit as we approach 2 from the left, or 1 from the left, excuse me?
2.
Also 2, which means the limit at 1 is
2.
2. We would say that doesn't exist if the first 2 don't meet, right? Now, what is the difference in question 4? Question 4 is asking me what is the function value? So that's where I'm going through, and I am looking at 1. What is the function value at 1?
-1?
-1. So using these 4 numbers, I can tell whether my function is continuous or not. So I'm going to walk through this checklist with you. So the checklist, statement 1, and now we are specifically talking because we're looking at questions 1 through 4 about x equals 1. The first thing that has to be true is that f of 1 exists. All right, so look at these 4 answers right here. Does f of 1 exist?
Yes.
Yes. Because of which number? Or which number answers that question?
-1.
This one right here. Yep. F of 1 exists and it is equal to -1. So check, number 1 works. What we just said on our continuous notes is the second one is that the limit as x approaches 1 must also exist. All right, so tell me, is that true?
Yes.
Yes, and that is answered by question 3, right? Our limit does exist, so check number 1, check number 2. What we then said on our continuous notes that we just talked about, number 3 is that the limit as x approaches 1 must equal f of 1. Is that condition met?
No.
No. And how do we know that? Because we are looking at those 2 numbers. Are those 2 numbers the same? No. Therefore, we would say, and you're not, how I will have set this up on a test is that you're going to choose from like drop down menus. So you're not going to have to write down this notation, but it's not a bad way to think of it. I would say as my answer, f of x is discontinuous at x equals 1 because that the limit does not equal f of 1. Okay, so that would be my reasoning on that. In order for it to be continuous, all 3 have to be met. Any questions about that? Because it's kind of a weird concept to begin with. All right, so let's try that again with 2. 2, f of 2. So now we're going to look at 5 through 8. So looking at x approaches 2 from the right. What's going to be my limit as x approaches 2 from the right?
-3.
-3, good. Limit as x approaches 2 from the left?
2.
2. What does that mean about my limit at 2?
It does not exist.
Does not exist. And what's my function value at 2? 1, 2, 3, 4, 5, 6, 7, 8.
Yep.
Just close that up here. Yeah. All right, so going through that checklist again, things that must be true for it to be continuous. And I mentally or actually walk through this checklist every time. F of 2 must exist. Is that true? Do I have f of 2?
Yes.
Yes, it is 8. Okay, I have a value. Second one, the limit as x approaches 2 must exist. Is that true?
No.
No, because question number 7 does not exist. So when you go through the checklist, once you get to one that does not work, just stop there. So if the first one is not true, then you're done. You're done checking. It's not continuous. The last time we had to make it all the way through all 3 to get one that didn't work. So here I lost it on the second one. So now my answer to this question, is this continuous? I would say f of x is discontinuous at x equals 2 because why? What reason didn't work?
The limit doesn't exist.
Right. I would say the limit at x approaches 2 does not exist. Yes, ma'am.
I remember at like some other point in math, if we had like a closed circle on top of an open circle, it kind of like filled it in, so it was like
Yep.
continuous. That's not applicable here, correct?
It could be if you were given a piecewise function that does meet in the middle, that's when it would still be continuous, even if it's piecewise and comes together. So it
Okay.
could happen. You probably wouldn't be able to see it visually on a graph because you would just see the closed dot. But if you were graphing your own piecewise function, that could come up. Yes.
So like going along with that, if there is a hole in a there can be a hole in a continuous.
There cannot be a hole in a continuous function, no,
Okay.
because that would violate the first rule. Let me
Oh,
see if I can find a different one. Just for the sake of argument, I'm trying to find one that violates every single rule. So just hold. I don't want to do all of these for you guys. That would be the same reason. Most of these are going to be limit doesn't exist, or the third condition, the f of the value does not equal the other one. For the sake of argument, let's just do one more of these. And then I'll try to find some examples where it's not continuous because of the other reasons, or it is continuous. Sometimes you're going to walk through it and say, this works, this works, this works. All right, we're continuous. Let me look at, let's look at questions on this one, 17 through 20. Oh no, that's a good one actually. I picked a good one, yay. All right, 17 through 20. If I am going through limit as we approach 8 from the right, what would be my answer to that?
Infinity?
Limit as we approach 8 from the left.
Also infinity. Right?
Also infinity. So you could potentially make an argument right here for what answer for 19?
Infinity.
Since those are both infinity, you could tell me infinity, but what we need to remember is that infinity is not something you can actually equal. So you could also put DNE for that, because technically speaking, you're never going to get to infinity. So it's not an actual number you can get to, but either or I would accept on 19. Now, what is my answer for 20? F of 8.
No solution.
No solution, or 0 with the slash through, right? So if I'm going through my checklist now, my checklist, first thing is f of 8 exists. True or not true?
Not true.
Not true, because of what we just answered in question 20. So do I have to check the other two?
Nope.
Nope. So I would stop right here and I would say f of x is discontinuous at x equals 8 because f of 8 equals undefined, or doesn't exist. You could say either or. Okay. Is this starting to make sense, kind of the checklist we're walking through? And that's really all there is to proving something continuous or discontinuous. Do we want to do another one on here, or do we want to do one with the equation?
Equation.
Okay, we're going to flip back to page 307. Uh-oh, I rotated my entire view on this. Look at this. My notes are sideways. All right, so let's take a look at example 1 on page 307. Okay, so for something like example 1, this, if you're given an equation, it's just going to say find the values at which it is discontinuous. So if we are thinking about that, think visually here, or things that we've seen on the other graph. What kind of things make a function discontinuous? What's this? What did we call this kind of thing right here?
Hole.
A hole in the graph makes it discontinuous. What other things that we just saw at f of 8 on that other graph made it discontinuous? What do we call those when it goes like that?
Asymptote.
Asymptotes. So holes, asymptotes, and then this picture right here in the middle with the two pieces that don't come together, that tends to be a piecewise function where it doesn't meet. So that would be something I'd worry about for something like example 3 and example 4 here, but maybe not example 1, which is not a piecewise function. So on something like example 1, my mental state right now is I need to worry about holes in the graph and I need to worry about asymptotes. We may or may not use a calculator to see what a graph looks like for example 2. That may not be something you recognize. We did talk about them, and we are going to come back to that in a second when we talked about parent functions on that. But when we did stuff like example 1, which we just did again last class, we said the first thing that we do for rational functions is factor everything. Okay, so if we factor top and bottom here, what is going to happen for me?
You're gonna cancel
Minus
out
3's
the
cancel out.
Okay, so my x minus 3's cancel out. Now, what does that tell me?
You have a
Yeah.
hole at x equals 3.
Okay, so I have a hole at x equals 3. My simplified version is then 1 over x plus 3. What other thing am I going to have to worry about in this equation?
vertical asymptote.
Mm-hmm. I'm going to have a vertical asymptote at x equals what?
-3.
Negative 3.
Negative 3, right? Now, we still have to give reasons for these. So we said our function is discontinuous at a hole. It's also discontinuous at a vertical asymptote. So these are two places that my function is going to be discontinuous, but I still have to think through my checklist. So if I'm thinking about the hole at x equals 3, which of my 3 reasons is that going to violate? Am I going to have f of 1 or f of 3 does not exist? Am I going to not have a limit at a hole? Or is the limit not going to equal the function value at the hole?
F of 3 won't exist.
Exactly. A hole, there will still be, the function will still be coming towards the same value, so you're still going to have a limit, but there's just not going to be a value right there. So I'm going to say, I'm going to make my statement here and say f of x is discontinuous at x equals 3 because f of 3 does not exist. Well, I did not put not equal to, does not exist, like that. Or I can literally write the words does not exist. Then I would say f of x is discontinuous at x equals -3 because what's going to be the issue at -3? Which of my 3 statements?
The limit won't
Yes,
exist.
because at asymptotes, the limit does not exist because they go opposite directions. So I would say the limit as x approaches -3 of f of x equals dne, or the limit does not exist. Okay. Issues, problems, questions on that?
Do you only look at the
How would-
vertical asymptotes, not the
The
horizontal?
horizontal asymptotes are not going to change continuity because of them being a completely different. We state discontinuities at x values. Horizontal asymptotes are y values, so we don't use them as part of our discontinuities. Yes. Someone else had a question?
No, I think I figured it out. Because if we have 2 asymptotes going in the same direction,
Mhm.
from the left, it's like, let's say infinity, and from the right, it's infinity. But as a whole, it still doesn't exist because
Right.
you can't be.
But you're still not going
Okay.
to function value at that.
Okay, so it doesn't matter, like, finding out if there are like other asymptotes
No.
going with it. Okay.
Yep. They're still not going to have a limit there. And in fact, I could say that it's discontinuous at x equals -3 because f of -3 does not exist either. Because technically, I'm also not going to have a function value at -3. So I could give multiple reasons for that. I tend to give the first one that I come across.
That's fine.
How many do you typically want us to include?
So the way I'm going to set this up is actually going to be very similar to, and I'll just flip into homework so you can see this for the test purposes. It's going to be very similar to this question right here on page 308. Only I am not going to ask you to fill in all of these boxes. You are going to basically be doing these two columns. I wish I could, well, I guess I can write on this here. You are basically going to be giving me these two answers as drop-down menus. So you're going to pick continuous or discontinuous, and you're going to pick one of these 4 reasons. Okay. So let me just walk you through what this kind of looks like for one of these, because this will be your part of your homework, and then you can do that on your own after that. The input is just which one we're looking at. I probably will not do these A1 through A6 values. I'll just give you X values. It doesn't really matter. This one is very generic. But if I was just walking through, for example, I would say, all right, I'm looking at A1, whatever that X value is. At A1, this right here is asking you the function value. So at A1, where's my closed dot?
C
See what?
C3.
C3. Yep, that's my closed dot. All right, so then also still looking at A1, we're saying everything about A1. The limit as we approach this from the left would be what?
C1.
Mm-hmm. The limit as we approach this from the right would be what?
C3?
C3, which means what about the limit at that point?
Doesn't exist.
Mm-hmm. All right, so using that information, which is basically what we just did on the other graph, because you're not going to have to do this way, but I would suggest walking through those 4 parts: limit from the left, limit from the right, limit, function value. Is my function continuous at this point we've been looking at?
No.
No, right? So it would be, I would choose discontinuous as my drop-down menu. And then which of these 4 reasons is our reason for why it is discontinuous?
The limit doesn't exist.
The limit does not exist. So I would say B. Or if it was a drop-down menu, I would select that one. Now, why are there 4 reasons when I told you in there that there were only 3? I wasn't lying. There are only 3. This last one right here, this is not a reason for being discontinuous. This is the one that you choose for it being continuous. The limit exists, and the function value exists, and they're equal. So that last reason right there is not a reason for it being discontinuous, but rather if you chose continuous, that's the only reason you may choose for it being continuous, because it has to all be true. The function value exists, the limit exists, and they're equal. So does that table kind of make sense as to what you're doing? And that's like honestly exactly how I would have set it up on the test for you. That you are going to choose, I'm going to say, all right, at x equals -1, is it continuous or discontinuous, and which of these reasons?
What is C saying?
What is C saying? That is saying that the limit exists and the function value exists, but they're not the same.
Okay.
That would be something like A5, right there. I have a function value, I have a limit, but they're not the same number. Okay.
So if the dot was like filled in on A5, then the function value is C3, and then the limit is also C3.
That would be like A6.
Okay.
That's what you're looking at A6. So A6, you would say the function value C3 or C4, The limit's C4, therefore it's continuous because of reason D, because the limit exists, the function value exists, and they're the same number. Okay.
Miss Langer.
Yep.
Back on like the problem, like the actual problem, I guess, on example 1.
Mhm.
Could you explain, because I'm kind of confused at why the whole at 3, like how do you know what to say, like the f of x is discontinuous?
Because when we graphed these, we would have said, all right, so I have an asymptote at -3. Whoops, that's not a dotted line. I would have graphed that. I would have had a horizontal asymptote at 0, but that doesn't affect my continuity. And when we graphed that, we would have then had a branch up here. Okay, so just drawing a quick sketch. How did we draw a hole in the graph? At 3, we would have just said this, right? Well, that's exactly, visually speaking, what we said in the notes, that f of 3 does not exist. There's no value there. That's what a hole is
Okay, that makes sense.
by definition. So I'm visually thinking about that. And you could graph that if you wanted to, but let's quickly take a look at one of these piecewise functions just to give you another way of seeing the graphs. Mostly what I'm going to be doing with continuity is going to be where I give you a graph and you have to tell me whether it's continuous or not at those points. And here's the logical thing though in all of this. Remember that when we talked about continuity in the fall, because we said whether parent functions were continuous or discontinuous, we just said the basic idea of continuity is, can you draw that part of the graph without picking your pencil up? So if I'm looking in this graph at A1, logically speaking, I should say that's literally discontinuous. It's 2 separate sections. Logically speaking, at A5, if I was drawing along here, I would literally have to pick up my pencil to draw this up there. So continuity really depends on whether you're actually like picking up your pencil to draw the different sections. So you can visually, hopefully you are able to look at the graph and without even worrying about my conditions say, all right, it's discontinuous at A1, A3, because I'd have to jump over that hole, A4 because I'd have to jump sections, A5 because I'd have to jump over the hole, draw the other dot. A6 is continuous because I can draw that without picking it up. So that's more of a logical thing. I still want you to work through like the conditions to it, but hopefully you can at least tell some of that from the graph.
Fleininger?
Yep.
In the fall, did we do continuity like as a whole, or was it like
Yes.
from the x direction or like from the y direction?
Yeah, we said the graph was either the whole parent function was discontinuous or continuous because of one break in it. Yeah.
Okay.
So example 3 is a good one of a piecewise function. That will be kind of where I finish up here for you. Remember for piecewise functions, and I would probably graph these myself. You don't have to. Actually, let me show you without it. For the visual people, I'll show you with it. To check for continuity, I check, and at piecewise functions, I'm only worried about 2 because that's my breaking point. If there were multiple sections of the piecewise functions, I'd worry about where the sections came together. But for this one, my 2 sections come together at 2, so I'm only worried about 2. Just like when we looked at the rational function above, we said we're only worried about the holes and the vertical asymptotes. So I have certain areas to worry about for each type of function. Piecewise functions, it's where the sections come together. Rational functions, it's vertical asymptotes and holes, stuff like that. But you can always check a graph for these. But for this one, then I would worry about the different conditions. First, does f of 2 exist? Can I plug in 2? And which section would I plug it into for f of 2?
The first.
The first one, because of the equal to, right? So I'd plug in 2 there. -2 times 2 gives me 4. What just happened to my thing here? Oop, cancel. All right. So I have a function value. The second condition is that the limit exists. In order for me to tell if the limit exists, I have to do the limit as we approach from the left. and the limit as we approach from the right to see if I can then get a limit. All right. So from the left, which section would I plug it into?
The top section.
The top section, which would give me -4. I would then from the right plug it into the bottom. So 2 squared minus 8 gives me -4 plus 1 gives me what?
-3.
Okay, so what does that tell me about the limit?
Doesn't exist.
Which then means that I can make my statement of f of x is discontinuous at x equals 2 because of what reason?
The limit doesn't exist.
Right. Limit as x approaches 2 does not exist. Okay.
The f of 2 not -4?
Oh, it should be. Yeah, thank you. Questions about that kind of process there? No? All right, homework is short for this. It is page, let me see what I actually made it. I definitely want you to do the table on 308. Let me see what else I put into this on the assignment page and see if I still want to do it because I can change my mind. Homework 9.5. 9.5. Let us see. I said nothing. Good. I'm a genius. I can make it up right now. All right, page. We want to do page 308. I want you to do through 10. Okay. And for 7 through 10, I would try to do it without a calculator, but if you need to plug it into a calculator to see what it looks like, go for it. Just remember for piecewise functions, how to type those into your calculator, and also that your calculator will not give you open and close dots. So you need to be understanding in piecewise functions where the open and close dots come into play. I would honestly try to do 9 and 10 without a calculator because whether you like graphing piecewise functions by yourself or not, you are going to get a better understanding of whether it's continuous or discontinuous based off of your own graph, not the calculators, because the calculator is not going to show you a lot of stuff on those. So these are actually pretty straightforward, these 4 questions. I think we should all be able to do them without a calculator. Okay? Any questions?